The deflection in magnetic field, how these radiation can deflect in a magnetic field. For this, you have to use a left hand rule. In the left hand rule, the first finger, the index finger, represent the magnetic south. That's the index finger, represent the magnetic south. The second finger represent the direction of the particle, direction in which the particle is moving, and thumb automatically shows the direction of the deflection. So you will apply, always use this left hand to find the deflection of alpha particle, and same thing is there, but right hand, the index finger represent the direction of the magnetic field, the second finger represent the direction of the particle, and the thumb is representing the force or the deflection. So for alpha particles you will use the left hand, whereas for beta particles you will use the right hand. So as you can see the next image, how we'll know that alpha is going towards the left hand side and beta is going towards the right hand side, and alpha and gamma without deflection, because gamma is not having any charge, so it is not deflected. But how to identify the direction of the alpha? So first thing, to determine the direction of the alpha, what rule we have to use on the left hand side? So the first rule, the left hand side, you will use the left hand for alpha. Now I'll try to apply the rule on the figure. The first finger, your index finger, should point towards the south. The index finger, the first finger, is a magnetic south. So the index finger, the first finger, is simply representing the magnetic south. What about the second finger? Your second finger of the left hand should represent the direction of the particle, alpha. Like which direction alpha is coming from. And your thumb automatically will represent the force or the deflection. So as you can see here, example, if this was not given, so if I apply the rule, Fleming's left hand rule, you try to apply the Fleming's left hand rule, first finger should point into. So your index finger should point towards the south. Your index finger should point in this manner, the arrow which I am drawing. That is the direction in which your index finger should point. And the second finger represents the direction in which alpha is coming. So alpha is coming up. So this is the second finger should point in this manner. So first finger towards the screen and second is upward. Which direction your thumb is pointing automatically? The index finger, the first finger, is pointing into, and your second finger is pointing up, the direction of the alpha particle, which direction it is coming. Where your thumb is pointing automatically, towards the right hand side or left hand side, when you apply a left hand rule. So whenever we are finding for alpha particle, the first finger pointing towards the magnetic field, the second represent the direction of the particle, and thumb automatically represent the direction in which the particle experience the force. So in this case, if for alpha particle, it will experience the force on the left hand side. So as it experiences the force on the left hand side, so alpha, which direction it will deviate or it will go, so it will move towards the left hand side. And what about beta? Beta will always move in opposite direction, but you can apply a rule here. For beta, you can use the right hand rule. the same rule is there, but instead of a left, we will use a right hand. So we'll use the right hand for beta. The first finger represents the direction of a magnetic field, second represent the direction of the beta particle, and the thumb will point towards the force or the deviation or deflection. So same way, when you apply the rule here for beta, so first finger should point in the direction as I'm drawing the arrow. So first finger should point towards the south. The beta particles are also going up. So beta particles are moving up. So we'll draw the direction of a beta particle also up. They're coming up. So index finger is pointing towards the south pole. And this is the direction of the beta particle. They are going up. So we'll use the right hand rule, index finger pointing south. So when we apply the rule, magnetic field, first finger magnetic field, which is pointing into, second represent the direction of the particle, which is going up. As a result, what will happen? That the deviation, the thumb is pointing towards the right hand side. So the beta particle will experience a force towards the right hand side, or they will deviate towards the right hand side. So direction in which alpha deviate and beta deviate, they are opposite of each other. And another thing you can see, when we compare their deviation or deflection, beta deflect more than alpha because beta is having a less mass, so it can easily deflect as compared to that of alpha particle. So another figure you can see here, the magnetic field is into. What is the meaning of magnetic field is into? It means south is into the paper. Like south is inside. So your index finger should point towards the south, which is into the same idea. The second represent the direction of the particle which is going up. So your index finger should point into first finger, second represent the direction of the particle which is going up. And when you are using for alpha left hand, so you will find that alpha will deviate towards the left hand side of the page. And for beta, the same rule is there. For index finger should point into, the second finger should point in the direction. And when you use the right hand for beta, you will find it deviate in opposite direction. As you can see here in the figure, alpha is deflected towards the left hand side, where beta is deflected towards the right hand side. And the deviation or deflection of alpha is smaller as compared to that of beta. Like beta is more curved as compared to alpha. And gamma, we don't have to use any formula here. Reason, because gamma is a neutral. It is not deviated by the magnetic field. So as you can see here, figure 11.1 shows a beam of alpha particle and beam of beta particle in a vacuum. The beams are about to enter a region of a strong magnetic field. The direction of a magnetic field is into the page. Suggests why the particle of suggests why the path of a particle in a magnetic field is always curved whenever objects are moving in a circular path, because there is a force acting towards the center. This is related to general physics. There is a force acting towards the center always. That's why the particle move in a circular path. But sketch the path for both alpha and beta. So always remember, whenever you have alpha particle, you will use left hand. And when you have beta particle, you will use the right hand. Only the difference hand will use, or you can work out on one and the other one will always be opposite. So if alpha particle is going up, beta will go down. If alpha particle is going down, beta will go up. So the index finger, the first finger, is pointing into The index finger should point into, the second finger will point in the direction of the alpha particle, and thumb will show alpha or beta depending on which hand we are using. If left hand alpha, right hand beta. Thumb will shows a deflection or the force. So when we apply the rule here for alpha, we will observe that alpha particle will go up and beta particle will go down, and the deviation of alpha is less than deviation of beta. So in the question, a beam of ionizing radiation contain alpha, beta, and gamma is traveling left. It's traveling left to right. So from the left hand side to right hand side, and the magnetic field is acting into. So if magnetic field is acting into, this is related to the previous one. When as it's the same question, magnetic field is acting into and the particle is moving from left to right. The question is, if alpha particle go towards the top, so deflection of a beta should be opposite. So where beta will go, if alpha is going up, beta will go down. And deflection of alpha is small, but beta will be large. And for gamma, because it does not have any charge, so it is not deflected by electric or magnetic field. A beam that consists of both alpha and beta particle is passed through a region of a space where the magnetic field is perpendicular to a direction of the beam. State two ways in which deflection of alpha differ from beta. So number one, their directions will be opposite. Like if alpha is going up, beta will go down. If alpha is going down, beta will go up. And number two, alpha will have a small deflection. And beta will have large deflection. So that's how they are different from each other. In this question, figure shows a beam of radiation that consists of alpha particle, beta, and gamma. And the beam enter a very strong magnetic field. Complete the table below. Deflection. Is there any deflection for alpha particle? If any, yes. For beta, is there any deflection? Yes. And for gamma, direction. Gamma will be no. But now we need a direction of a deflection. Like first part, yes and no is not the answer. Yes and no is just to make you understand the question that there will be a deflection for alpha and beta, but no deflection for gamma. But now how to work out the direction? How to know the direction? For direction, we have to use a rule here. So if you, for example, if this was alpha, so we'll use the left hand. And in the left hand, your index finger, the first finger, will point towards the magnetic south. Your second finger represent the direction of the particle alpha, and your thumb will point towards the force or the deflection. The direction in which it will deviate, that is into the paper. And as I mentioned, if alpha is up, beta will be down. If alpha is down, beta will be up. If alpha is into, beta will be out of. So beta will be out of the page. And we can also work out for beta what we'll do. We'll use a right hand. Like alpha we use left hand. The same for beta, we'll use a right hand. The index finger, the first finger, represent the magnetic south. The second finger represent the particle beta, and where the thumb will point, that shows a deflection or deviation. So when you apply the rule, next the charge, if they carry, what charge alpha carry positive charge. What beta carries, it carries a negative charge. And what is the charge of gamma? There is no charge on the gamma. So state two ways in which gamma emission differ from beta emission. How gamma is different from beta. So this is, that whole table is a comparison. Gamma is electromagnetic radiation. It travels with the speed of light, but beta is actually electron. Gamma is uncharged, beta is negatively charged. Gamma does not have any mass, beta is having a mass. Gamma is having a long range, beta is short range. Gamma can be stopped by lead, beta can be stopped by aluminium. Gamma low ionization, beta high ionization. Gamma is not deflected by electric or magnetic field, beta is deflected by electric or magnetic field. And there is no change in atomic number or atomic mass, but in a proton number changes when there is a beta emission. In this question, as you can see, we have three detectors. One is at A, one is at B, another one is at C. Three detectors are there, which are passing, like radiations are coming from the radioactive source. We use a LED screen so that they can pass in a straight line. And then we have the detectors, the radiation detector are placed at A, B, and C, and they give the following reading. So 32, 543, and 396. And the radiation source is then completely removed. Like first, when there was a source placed in front at A, we were getting a 32 radiations. At B, we are getting 543 radiation, and at C, we are getting 396 radiations. But when we remove the source, there is no source placed now here. If there is no radiation from the source, what we get, it remains 32 or 33. For this one, it decreases to 30B, and this one, it decreases to 31. So the question is, from the data, deduce the type of radiation emission being detected, if any, at A, B, and C. First, at A, because at A, before and after, there is no change. So if we don't observe any change, because the radiations are coming from the source, if it was L, when we apply the Fleming's left-hand rule, if this was a alpha, A should receive alpha, because first finger represent the magnetic field, which is into, second represent the direction of the particle, and alpha, thumb is pointing up. But when you see the number of the counts before and after for A, it does not change. So A is no radiation from the source. Why no radiation from the source? Because the counts does not change. So actually it is from the surrounding. So all the radiations are from surrounding. Like source is not providing radiation. Otherwise, when source is there and when source is not there, there should be a difference. Then what about B? When there is a source, it was 543 radiations, but without source, it is 30. So it means the radiation has decreased. So what it, and the radiations are coming directly from source to B without deflection. So what kind of radiation at B? At B, it means it should be a gamma radiation. And what is the reason why we are saying gamma? Because there is no deflection. And what about C? You can observe it's a large deflection. And before it was 396 and now it is 31. So at C, which radiation we detect? We detect beta radiation. And what is the reason why there is a beta radiation? Because this shows a large deflection in the magnetic field. And there is a change in the counts with and without source. There is a change in count. Like here with source, it was 396, without source 31. Here with source 543, without source 30. So with and without source, because the counts, the numbers are changing. That's why we say that these radiations are coming from source. But for A, why we are not saying that radiations are coming from the source? Because with source or without source, the counts remain unchanged. Is it clear? Okay. Then the detector which we can use, there are different types of detector. You don't have to learn the working of these detectors. This is just an information. You just have to learn the name of the detector, not the internal working, how it works. So we have different types of detector. We have a GM tube. GM tube can be used as a detector for the radiation. We can have a cloud chamber, a Wilson cloud chamber. This is how a cloud chamber look like. This can be used to track the radiation, identify the radiation. This is how we see the image in the cloud chamber. And we can also use spark counter. This is called a spark counter, as you can see here. So this spark counter can also be used to identify the radiations. So this was about the radiations. As we discussed the magnetic effect of these alpha, beta, and the magnetic deflection and magnetic field for alpha, beta, and gamma.